to start? I mean,
Why? No. Cosa quello sbagliato?
this one is working.
C'è messo fare. Ok.
Should I start?
Yes.
Okay.
Actually, there are not many people outside, so maybe that's all.
Okay. I can start and I can manage. You can see. Okay. Hello all. And we are going to start the session again. So my name is Muhammad Hassan, and today I'm going to give a short talk on one of the possible vulnerability in uh, dynamic adaptive streaming over future internet architecture, which is ICN. So in particular, it's a QA degradation attack in adaptive streaming over ICN, and this work was also been accepted this year in IEEE WOMOM. So I have divided this talk in 3 parts in main. Like in the beginning, the introduction of ICN, which probably I will gonna trim a bit, and then a little bit introduction to how the dynamic adaptive streaming is being conducted nowadays, and then the architecture of dash over ICN, and then we will gonna discuss about what are the possible vulnerabilities in dash over ICN, and in the end, I will gonna conclude about what could be the possible mitigation approaches to solve this problem. So, just to skip that slide because ICN introduction is already been given, so it's basically a communication paradigm replacing host-to-host communication style into a request and response data-oriented model. Just to see what are the additional features in the ICN-based router in general are the content store, which saves all the content which are being once traversed through that router, and first the request or the interest in general matches the content store or cache of the router. If it can satisfy, if it has the match, it satisfies the router. Then the second additional feature is that pending interest table, which aggregates all the similar requests which are being received at that particular router. And the third one is the same FIB, which works similar to how the previous presenters have already been explained. So the importance of multimedia and in the current internet architecture, as it's been already been told, it's been increasing dramatically. But the point is, like, why ICN and the multimedia needed to be integrated, like, because both the adaptive streaming and the ICN tends to solve the problem of the bandwidth in a different approaches but try to perform to solve the same problem. How, like in ICN, it tries to name the video content itself and try to make the traffic demands local by the help of the caching, and adaptive streaming in general try to adopt the network conditions to satisfy the user with the best appropriate video quality or the best appropriate network condition. So in general, if we look in depth of how this adaptive streaming works, Dash is basically, as told before, is one of the most commonly used protocol for adaptive streaming, also by Netflix, YouTube, and several multimedia service provider. So in general, just a very quick view on Dash. It divides the video content into multiple chunks, which are also called segments. And then each chunk is being available in all the available representations or the qualities of that. And client tries to fetch one of the most appropriate segment in the one of the most appropriate representation so that it adopts the network condition. And this process tries to help the client to have most appropriate quality of experience in variable changing network conditions. The point is that here is that the part which is adopting the network condition is on the client side. So Dash is also similar to ICN in several ways. One of the thing which is why is both are client initiated or pull-based approach. And if we see the naming structure in one of the ICN project, which is CCN, we can see that the naming structure of the CCN supports the segmentation on the versioning segment part of the Dash elements. Suppose like this is the video. The video can also be represented in different representations naturally by default using the ICN naming schemes. Similarly, there are other factors which are common in both Dash and the ICN which make them more appropriate to integrate. Like both are responsible and trying to distribute the content into the network, and both are trying to satisfy the efficient replication and distribution of the content. Both are providing multiple sources support, and both are session-free, both are of session-free nature. If you see this architecture of Dash over ICN, in which the Dash client is trying to operate as a native ICN client, here adaptation logic is working on the client side, and ICN network and all the representations of the Dash multimedia are on the ICN node. So what happens is that same as in the Dash local, you try to use the MPD file, which is basically a media presentation description, to fetch all the representations as a manifest file to adaptive client. However, instead of the HTTP requests, it uses CCN URI schemes. There are several proposed works which try to prove the efficiency of this Dash model by saying that caching can lead to bandwidth availability in a more appropriate rate, and also if you see that availability of multiple sources also help this client to have much more better experience. If we move toward our problem, is that we found that this bitrate adaptation logic, which is basically the part of the Dash client which is trying to adopt the network, is unaware of the network. And in ICN, this can be a problem as well. How in this adaptation logic or bitrate resolution adaptation logic in general, if we say, works is on three basic categories. Rather, it tries to estimate the available network bandwidth by measuring the throughput on each and every segment, or rather it tries to check its own playback buffer level. So if it has calculated that the bandwidth estimation is enough to choose the next higher representation or higher quality, it can switch to the next representation or the video quality. Similar is the case of the buffer level, which depends on its own certain levels of the playback buffer, and then it chooses to switch to the next level. The third category is the hybrid or the mixture of both these categories. What we found here is that this Dash client in ICN has two main problems here. The number one problem is that Dash client is unaware that from where the content is being coming. Rather, the content is coming from the server, or rather the content is coming from any of the router from the cache. He is not aware of that. Since both of these all of these bitrate adaptation logics are purely client driven. So Dash will gonna change its resolution, and no matter if the content is coming from any of the different source, or it is really a bandwidth change in the network condition. This challenge we utilized or we exploited to make the behavior of the bitrate adaptation logic to calculate him as a false bandwidth estimation. How we tried to do that, we used two of the most fundamental ICN characteristics, which was, as I told before, one is the caching, as already been told as well, and one is the interest aggregation. And we try to use these two features in such a way that we wanted to make RTT variation for a dash client in a single multimedia flow. Since just as in this figure you can see that what we wanted to do is to make a variation in a single flow so that this cache hit or a pending interest table can make the interest rather to hit on the router or on the pending interest table. So that in a single flow, we wanted to make a dash client have different RTTs for the very frequent segments. What we will gonna have by doing that? There are two cases in that. If we try to increase the bandwidth by sharing some segment on the dash, it also benefits the client by increasing the QA. So since that caching can also reduce the bandwidth requirements for the producer. But also with this thing, we can create a false bandwidth estimation for the user. But how this can be a false bandwidth estimation, this is a part. Like if we can degrade the QoE of the whole video session from that false bandwidth estimation, we can make the dash client to behave that this false estimation, this estimation is not correct, and he will gonna switch to a different resolution. To do that, what we try to do in a simple way, we extracted all the URI streams from the manifest files, which are available because of the dash standards to everybody, all the clients. And adversary tries to issue the interest in a sequence with the consecutive gaps in such a way that we wanted to make the client hit on the router rather on the cache or on the pending interest table after every few consecutive segments. And what we try to achieve with this way is that we try to make the client switches to different resolution, which should be very low and very high after every few seconds. For this, the matrices, which were two of the main matrices for quality of experience in multimedia, which we try to manipulate, is the one is that user wanted to have less number of frequencies of switches, as explained earlier by the professor as well, that maybe user don't wanted to see the video in a very high resolution for a multiple durations of time. Instead, he wanted to have a very stable video quality for a long duration. But also, this frequency of oscillations matters if you increase the amplitude of this oscillation from a very low to very high. So what we try to do here in this attack is that we try to populate or cache all the resolutions of the segments. We don't know that on which network condition this dash client is currently behaving. So since we populated all the resolutions on the intermediate routers, he believed that he is available with extreme bandwidth. And what we saw in the results is to have enormous oscillations between very low and very high. These are the results which we got. We used the simulator. One of the implementation of ISIN is named data networking, and we use NDM SYN for that. And we were able to see that in this figures, not only we are having increase in the oscillation, in the frequency of the oscillation, but also we are having high amplitude difference between the oscillations. What we saw by using these two coding format, which is most commonly used, advanced video coding and scalable video coding, that only the buffer-based scalable video coding is favorable in ISIN format. But this is also a question that how many devices can be integrated with buffer base, considering the space of the buffer as well, because there are certain devices which are memory constrained, like mobile devices and iPads, etc. So in all the cases, we can use this buffer-based approach or bit rate adaptation logic. So let's conclude this talk. So what we identified by this work was 3 things needed to be considered before the integration of DAS and ICN environment. The one thing is the inherent network caching or dynamic network caching, which we saw that also is helpful, but it can also may lead to false bandwidth estimation. The number second thing is the ICN support for multipath delivery can also be a cause of false bandwidth estimation for adaptive streaming. And the third thing on which we also worked is that the transport mechanism in ICN and the aggressiveness of transport mechanism in ICN because of the caching is also a problem for Dash. Since we have seen that we try to create an RTT variation just because of the caching, there need to be fairness in RTT for one single flow. Therefore, these 3 were the possible directions we needed to be considered before the integration of Dash. In further work to this, we also tried to design one approach to maintain the fairness in the RTT on the Dash client, and that work is also being currently submitted. So that's all for my talk. Thanks. Any questions regarding this? If no questions, then okay, we have the next.
Aspetta che ti introduco brevemente. Okay, next speaker will be Fabio De Gaspari from University of Sapienza, Rome. He's actually working on ICN, SDN both, and he's a PhD student.
Hello everyone. So, as Eleanor already said, I'm Fabio De Gaspari, a PhD student from the Sapienza University in Rome, from the Department of Computer Science. And today I'm going to present work I did on access control in information-centric networking, in collaboration with Cisco and with Mauro Conti, of course. So I gather that you heard a lot already about information-centric networking today, so I'm not really going to give you an overview of this, since you heard a lot about it already. Just very briefly, of course, you know that it's a new network architecture that is based on content rather than on end-to-end host communication, and most important thing in ICN is content, and each content has a unique name. Contents are retrieved through this unique name, and the contents can be cached in the network in order to speed up subsequent retrieval for the same content. I'm not going to go over this again. Yeah, here we have a very brief example of this, blah, blah, blah. Okay. Talking about access control. Well, first of all, ICN for IoT. The important thing from my point of view of ICN is its applicability to IoT. The characteristic of ICN make it a really good fit for the widespread adoption of the Internet of Things. This is for a number of reasons. So first of all, we have that since thanks to ICN, we have that in general, users' requests can be satisfied by the network. Therefore, there are less requests that go all the way to the producer. We have that the actual load on the content producer is reduced. And this can be a great advantage in the case of IoT, because less requests received by IoT devices translate into increased battery life, which is a great constraint in the case of IoT. Moreover, ICN generally provides easier integration in the network for the things, since first of all, it eliminates one of the biggest problems, which is the addressing of the device. Of course, in IP, you need to be able to address each of the IoT devices. In ICN, we don't have this problem because what we actually address is the content they produce, which is much, much easier, of course. And moreover, ICN is a simpler protocol compared to IP, so which is, again, another advantage when you have to implement it in resource-constrained devices. Finally, of course, the increased availability that ICN brings to the table is a great asset in the context of IoT, because once again, resource-constrained devices can fail way more often than traditional servers and traditional computers. Therefore, having a backup mechanism to still be able to obtain content, in this case from the network cache, even if the producer, even if the IoT device itself is not available, is of extreme importance. However, there is one considerable problem when we consider security in ICN, and that is the problem of access control. So if we consider a standard ICN request response phase, here we have, for instance, an authorized user that is requesting to the producer a protected content. So the content A is protected content that should be accessed only by a set of authorized users. So I don't know, some users that are subscribed to a particular service, for instance. Well, of course, this is a problem in ICN because since we have that ICN routers can actually cache content in the network, well, whenever an unauthorized user requests the same content, the same protected content, well, the ICN routers just reply and giving him access to the content because, of course, the ICN router cannot have knowledge for each possible content of each possible content producer, which are the users that are authorized to access this content. So an ideal access control protocol for ICN has a number of requirements, a numbers of properties that are necessary for it to be acceptable. Well, first of all, of course, it needs to preserve the properties, the important properties of ICN, because otherwise there is no point in using ICN in the first place. So it would be such an access control protocol should provide efficient network caching, location-independent routing, and it should maintain increased availability of ICN, which means that any authorized user should be able to retrieve any copy of the protected content in the network and be able to access it. Moreover, of course, it should have a low overhead because otherwise it would not be practically usable. It should allow for revocation of access, obviously. And we would like it to also provide some form of trader tracing, meaning that if an authorized user discloses his access credential to a third user that is unauthorized, well, if we obtain this credential, we should be able to trace it back to the user that actually leaked them, so to our traitor. These requirements in the context of ICN are rather complicated to obtain altogether because they kind of seem at odds with each other. So for instance, we want to maintain caching, availability, and still provide revocation. Well, this is pretty challenging. I mean, it would be extremely easy, for instance, to obtain revocation just by using, for instance, a tunneling solution. But of course, they would be very bad for caching because the tunnel would effectively destroy network caching because only the two end hosts, so the producer and the authorized user, would be able to would know the key used in the tunnel, and any other user wouldn't be able to retrieve the tunneled cached copy of the content. Moreover, again, interaction between the producer and the authorized user decreases availability because if every time an authorized user wants to retrieve a protected content, he has to obtain some information from the producer. This means that the content is effectively only accessible whenever the producer is online. So if the producer is unavailable, the user can retrieve the content, but is going to be able to access it if it requires some information from the producer. On the other hand, we would like, for instance, to have low overhead and at the same time provide tracer tracing and revocation. How can we obtain all these properties? Well, obviously, one of the most used techniques when you talk about encryption-based access control is hybrid encryption. Well, hybrid encryption has a considerable problem, which is that, obviously, hybrid encryption provides you low overhead, but it has a considerable problem from the point of view of revocation. Because I assume you know how hybrid encryption works. Basically, we used a symmetric encryption algorithm to encrypt the content that we want to protect. Then again, we use a public key encryption algorithm to encrypt the symmetric key that is used to encrypt the content. So revocation is particularly challenging in this scenario because, for instance, an unauthorized user can just save a local copy of the symmetric encryption key, and basically will always have access to the content this way. Moreover, it can also leak this symmetric key to an unauthorized user, effectively giving access to the content to this third-party unauthorized user, and it will not be traceable because the symmetric key is the same for everyone, so we cannot know who leaked it. In our work, we specifically focused on access control in ICN for IoT, for the Internet of Things. This is for the reason I said before, because ICN is extremely important from my point of view for IoT, so we wanted to provide a solution in this particular context. Here you can see the system model we used in our work. We have basically three actors. We have the producer, which is the IoT provider, basically the actor that controls and manages the IoT devices, which are generating our data. We have an IaaS platform, which can be cloud computing or which can be fog computing. And we have third-party users which are running applications on the IaaS platform. So in this setting, what we want to do is we want to provide access control for the content that is produced by the IoT provider with respect to both the IaaS platform and the user running application on the platform. Our security model, in our security model, we consider that there is no trust relationship between the producer and the user, nor between the producer and the network or the IaaS platform. However, we do assume that the IaaS platform is at least honest but curious, meaning that they're going to try to obtain as much information as possible about the content, about the content published by the producer, but still they are going to follow the protocol. So this system model can be, for instance, applicable if you consider the case of a smart city, when you have a very big deployment of IoT devices in a well-defined geographical area, and you have third parties that want to access and process this data, and to do so, they exploit the computational power and storage that is provided by IaaS platform. The main idea behind our access control protocol is that we want to separate the information that is required in order to decrypt the content and obtain the clear text. So in our protocol, neither the infrastructure as a service platform nor the user by themselves have enough information by themselves to decrypt the data to obtain the plain text. Moreover, in our protocol, we use the IaaS platform as a kind of TPM, so Trusted Platform Module, and we do this in order to be able to perform some computation outside of the user space. So that basically this allows us to keep some information private, to keep some information outside of the scope of the user. As I said before, this to implement the split information required for decryption. We use ciphertext policy attribute-based encryption in order to provide fine-grained access control. I assume you know how ABE works. Moreover, in order to provide traceability to ABE, which is a considerable problem, we exploit once again the IaaS platform. Finally, we use layered encryption coupled with secret sharing between infrastructure as a service platform and the IoT producer to secure hybrid encryption. So this is an overview of our protocol, a high-level overview. There are more details, but of course, it would be impossible to show it in a single slide. So our protocol basically has three main steps. We have the publication step, which is here you see on the left side, which is done by the IoT provider, by the producer. Then we have a first decryption step here, which is done by the IaaS node, and the last decryption step, which is done by the user's application running the IaaS node. As I said before, it is necessary to keep this split information between the IaaS and the user in order that so that neither of them by themselves can decrypt the content. So, first of all, of course, we have the plaintext context M, the two encryption keys, K and R, because as I said, we use layered encryption. And the first step is to encrypt the plaintext content twice before publishing it into the network. Subsequently, the two symmetric encryption keys are themselves encrypted by using attribute-based encryption before being published. Moreover, for the second key, R, we further encapsulate it using the secret sharing between the IoT producer and the IaaS node. On the other side, on the decryption, we have that the first step, of course, is to retrieve K prime, C prime, and rho prime from the network. And then the first step is to decapsulate rho prime before using AB decryption. So this encapsulation and decapsulation step are extremely important because if you consider a user, a single user, without the intervention of the IaaS node, this ensures that the user will never be able to obtain M by itself without interacting with the IaaS node, as we said before. This is because the user has no knowledge of the secret share between the producer and the IaaS platform. Therefore, it will never be able to remove this encapsulation here. Therefore, as a consequence, it will never be able to obtain R, and it will never be able to strip the outer encryption layer on C prime. On the other hand, here we have that the ABE decryption performed by the IaaS node is done using a special delegate key, which is basically the key, the secret ABE key of the user, stripped of some information such that it can be shared with the IaaS node. This step is fairly important and is done for the reason that in this way, we are able to prevent the user from ever seeing R. As I said again, this is important because if the user ever managed to know R, then he would be able to decrypt C prime by himself, knowing also K. We do not want this because we want to keep the information separate for a reason we'll explain later. So after this AB decryption step, which of course is successful only if the key of the user is authorized, only if the key of the user matches the encryption policy that was used by the producer. The IaaS node performs a first level symmetric decryption in order to obtain C and forwards it to the user's application. The user's application uses its full AB key in order to decrypt K prime and then strips the last layer of encryption from the content in order to obtain the clear text. So our protocol has a number of properties, which are basically the properties I listed earlier. First of all, it preserves network caching, location-independent routing, and availability. This is thanks to the use of symmetric encryptions. Symmetric encryption allows us to have a single copy of the encrypted content in the network and encrypted under the same key. So any authorized user can use this single encrypted copy in order to obtain the plain text. So this means that effectively we are preserving caching, location-independent routing. Availability is preserved because all the data, all the pieces of information necessary to obtain the plain text contents are published in the network. We have K that is published, rho prime that is published, and C prime that is published. So effectively, all the information needed to obtain the plain text to perform decryption are published in the network. So there is no interaction whatsoever with the producer in the decryption step. Our protocol is efficient, well, as I will show you later. Our evaluation and provides full traceability. The full traceability property is achieved thanks to the fact that the IaaS node accepts only well-formed delegate key. So if you remember this step here, where we have the ABE decryption at the IaaS, it's extremely important that this step is done by the IaaS and not by the user, because this allows us to restrict the keys that the IAs accept only to well-formed keys. So the user cannot modify the key in such a way that it cannot be traced back to him. So this step here means that if an authorized user wants to leak his key to an unauthorized user in order to provide him with access, he has to leak exactly his key without any modifications, because otherwise this decryption step would fail. And since the key cannot be modified, we are able to trace it back to him easily. Finally, we can provide efficient revocation by embedding the revocation itself in the access policy with which the two symmetric keys are encrypted by using ABE. And the use of hybrid encryption and the requirement of very few ABE attributes allows us to maintain a very low overhead. Going over to the evaluation, here we have a graph showing the size overhead introduced by our protocol. We see a breakdown of the different components. And while our protocol introduces some overhead for very small contents, so for instance for 1 kilobyte contents, as the content size increases, the overhead introduces is negligible, because that is due to the fact that the overhead introduced by the two symmetric keys is constant and is not dependent on the size of the content itself. Therefore, the bigger the original content is, the lower the overhead introduced is, and up to the point where it becomes negligible. From the point of view of computational complexity, we have on the left we have a graph showing the overall consumption and publication time required by the protocol, while on the right we have a breakdown of each component. So as we can see on the left, in case of both consumption and publication, the overhead remains fairly small, even for contents of even for big contents like 2 to the power of 28. We still have the overhead both of publication and consumption are both under 250 milliseconds, which is acceptable. On the right, we see the breakdown of the computational overhead of each step of the encryption-decryption process, and we see that the main component of the overhead for bigger size of the content is the symmetric encryption and decryption steps. This is expected since symmetric encryption and decryption increases linearly with the size of the content that we are encrypting, while the overhead introduced by the ABE operation remains constant, it's independent of the size of the content. Okay, so concluding, we have, of course, as you have heard today, ICN has a great potential, and many big companies are behind it, which is always a very good thing for new protocols and new architectures. However, it still does require more research before it can be widespread adopted. In particular, from the security point of view, we concentrated in this work on access control for IoT in ICN, but the general problem of access control in IoT is still need to be effectively tackled. Our protocol can be extended to a general scenario, but we need to make some concessions either from the security point of view, or we need to strengthen some assumptions by using DRM or things like this. So maybe it's possible to have a protocol that does not require this stronger assumption, but still provides full access control in this situation. Another very interesting security problem in ICN is the problem of, for instance, confidentiality. So, of course, in ICN we have interests, and the exact content that you want to retrieve is written on the interest. So anybody that has a view on the network can know exactly what you're asking for, so your ISP. This is another considerable problem that, in my opinion, need to be solved before ICN can be adopted, because we don't really want, for instance, our ISP to know exactly which content we want at any time. So, yeah. Still more research to do, and yeah, that's it. Thank you, and if you have any questions.
Last one, but also the best one. Okay, so Ankit is a PhD student in Spritz Group. He's working on SDN, software-defined networks, and I leave the floor to him that will definitely explain this future internet better than me.
Thank you, Eleonora, for the introduction, and thank you for the audience for being present for my presentation. And thank you to the other speakers for their interesting talks during the day. However, during the entire day, the talks focused on ICN and CCN, but there is another actor in this area which is shaping the future internet, and it's called SDN. Probably most of us know about it, but those who don't know about it, that's why my presentation is for. So my presentation is divided into 3 parts, and while designing this presentation, I kept in mind that there will be young researchers that would like to learn something about it. So my presentation is jargon-free, equation-free, tension-free, so just relax and enjoy the presentation. I hope this will be one of the most important takeaway from today's workshop. I hope you will like my presentation. So, starting with the traditional network, we had boxes which were really, really dumb from the perspective of the operators. They consist of a data plane, a control plane, and a management plane. The first 2 things, data plane and the control plane, are bundled in a box, and nobody can do anything about it except the company that manufactures it, which means you buy a device, but you have no control over it. I'm sorry to say, but there is a popular company, I would not call the name of the company, but you buy their cell phone and probably you don't have much freedom to do anything about it. On the other side, there is another open source phones which allows you to do a lot of things on the go. So the data plane, what it stands for, this term refers to all the mechanism of the device that forwards your packets. The idea is just to stream the packets, forward it, filter it, buffer, mark, or do some other things related to the packet forwarding. The control plane, on the other hand, is the mind of the devices, which means it takes the decision and data plane follows it. On the other side, there is something called management plane, which is where the network operators comes into in the picture. It's that they configure the devices, how to communicate with each other. Mostly, the drawbacks of the traditional networks is that their cost is very high effectively, because after a while, like after 5 years or 6 years, the devices that you purchased before become outdated and you need to buy new devices, which means you invest some money and after a few years, probably they are out of date. Secondly, is that you cannot program them. You cannot change the logic running behind inside the box. And mostly innovation comes from the vendors, like big players, Cisco, and other big companies. And from our point of view, like for the researchers' point of view, we cannot do a lot about except the simulations, which probably the companies might not accept, because we are doing in simulation and they will say, okay, you did simulation in a laptop, probably we don't even accept it. So this is where SDN comes in. Software-defined networks takes the brain out of the network, out of the devices, and creates it in a software, which means you plug in a laptop, you write an algorithm, maybe in Python, maybe in Java, maybe in C, or whatever language you prefer to write your programs in. Okay, it should be a proper programming language. And then you can design your routing algorithm and just connect all the devices that you buy, and they will start to follow your program that you write. Which means if you want to change something in your network, you change your program, and there you go. Instantly, network programming in your hand. So the benefits of SDN are that you design your algorithm, you change the computer program, you restart the controller, and it will start working as you wish it to work now. Second is more flexibility is given to you, and you can actually adapt or create or do many changes whenever you want, however you want. Finally, the third is that you can change the logics, the innovation at each layer of TCP/IP networking stack or the stack that the system is following. So this is the broad overview of SDN. Don't look too much into the slides. I'm going to speak something about each layer and in very easy terminologies. So the infrastructure layer is the layer where you put your hardware. Then there is a controller layer where you put your program or computer software, which is the controller, like the framework of the controller. And the third is the application layer, which runs your application or your logic behind your routing or your forwarding or your firewalls. So this is how a system works in SDN architecture. Let's imagine there is an imaginary host called host 1 and it wants to communicate with host 2. So it starts to send a packet to saying that, okay, I want to send a packet to H2. This goes to the switch, and because the switch has no idea what to do, it asks the controller, okay, tell me what I have to do. So controller decides that, okay, I see that maybe host 2 is on the right of your side. Please forward this packet to the right side of your device. And send this rule to the switch, and accordingly switch sends or forwards these packets to H2. And on the way back to the reply, if H2 replies, it will follow the same procedure, but this procedure will be just one time, because with this kind of rule, the switch learns where H1 and H2 are. So next time a packet comes in the network, switch does not need to ask host about the location of the host 1 and host 2 from the controller. So which makes that, okay, systems becomes autonomous once it obtains the rule. This is just a very high level, I would say, the working of it. The controller could be centralized controller or distributed controller, which means you can have just one controller which is running in the network, or you can have multiple controllers which are running in the network. It depends upon how you want to design your network. Now, the important thing is where I want to focus in this presentation are the open issues that you might focus on, or the issues which are in the research domain that people are working around. I hope the figure is clear. So according to my understanding, I think also the literature confirms that there are 4 directions broadly that we can investigate in the area of SDN. First is the performance issue, the performance of the hardware, the performance, how system works inside. The management issue is like how to manage controllers in the network. Of course, security issues, security at various levels, and the reliability issue. I'm going to go one by one through each of them. So the performance issue is like CPU power. How much CPU power do you think is okay for a switch to have built in? Because more computing powers mean more cost of the device, or less computing power means less performance of the network. So this is a trade-off where we need to think about it. How much CPU power should we invest, or should the vendors put into the devices? So this is not really a research issue, but this can deal with other things that are related in terms of performance of the network. Another thing is the table where we store the rules. How big do you think a table should be like? So optimization of flow table is another thing that we can have a trade-off on. Next is, on the switch, how big the buffer size should be. If a size of the buffer be very, very small, then you have more packet loss, and the performance of the network again will suffer. And finally, the bandwidth between the switch and your controller also decides the performance of the network. Also, how the new flows are handled in the network affects the networking performance, because if the band is congested too much, if the switch is asking so many queries from the controller, there will be a congestion and the performance will go down. Another thing is how you store or how you look up how you search in the box. It's another thing. If you use static RAMs, which are off the shelf, which means you have latency within the hardware because the device needs to look for a memory which is off the shelf. So this will increase the latency in the access. Or could be the TCAM, which search for using a tuple, which is right now is used in SDN actually. Now the other issues are management issues. How do you partition your controller? How do you, the control plane? How would you like to distribute, do you want every controller, every switch to be governed by a single controller, or you want multiple switches to be controlled or governed by multiple controllers? Another thing is how you want to partition your controller area, like horizontal controllers, which means each controller is at the same layer with the another controllers, or you want to do a vertical partition like a master-slave mode. There is a controller, there is another super boss, and then another super boss. This could be something that we can investigate, and there is still no standard through which we can, which is well-known standard, I would say. Security issues are mostly on the switches, and the basic idea is to fake traffic so much that your switch keeps on wasting time in generating flows and asking the controller. Actually, this has consequences, because if a system has more flows, forced flows, then your switch will be investing time in asking the controller, which means it will generate more traffic towards the controller, which means it might congest the controller to switch link, which also means that your controller will spend more time in processing all those flows. So basically, if the attacks is targeted towards one part of the network, then there are consequences which are related to each other. Reliability issue is like what happens if the link fails in the network. So if there are some failures, how your system is going to take control or is going to overcome those failures. What happens if the controller itself fails? Or what happens when there are some switches which are updated frequently and some switches which are not updated frequently? So these are some questions that I kept in mind to share with you. And these are the references that I used to make the presentation. Thank you so much. Anyways, there is a link at the bottom. You can always write to me. I mean, there is my email address. So if you have any queries, you can write to me or you can ask right now. Thank you so much. Sorry, it's my website. I explained very well. Question? Mm-hmm. Mm-hmm. You mean the question is, what are the additional advantage that that the SDN can provide over virtual LANs? So the idea of virtual LAN is to create, so you have a fixed chassis on your device. So device has fixed number of ports. So virtual LAN creates virtual subports, and the idea of SDN comes just to make the functionality of the network. SDN is going to work at the same pace as TCP/IP stack. But, I mean, there is no additional thing that SDN provides to the network. It's just the way how you organize or how you manage the communication within the devices. So I would say SDN will not going to give any additional feature as compared to VLAN, according to my understanding. I hope that clears your question. Oh, okay. So in SDN, there is nothing called switch, nothing called router. If you go in the TCP/IP layer, there is layer 2, you have switches, and layer 3 are generally routers. In the case of SDN, layer 2 and layer 3 are mixed with each other. So your switch, which is not actually, I mean, it's not correct to use the switch terminology. The box that you have in the network can act as a layer 2 switch, or can also act as the layer 3 router. It depends upon how you write your controller program. So if you want to match over IPs, it can work as a router, or if you want to match on the data frames, it can work as the layer 2 switch. So in this particular case, SDN vanishes the boundary between layer 2 and layer 3.
Okay. So thanks for being here. I hope you enjoyed the talk. There has been nice, talks, opportunity for discussions. Hope also younger student will follow up with interest in the field, continue the research. There are of course opportunities to collaborate with our research group, hopefully with Cisco. Collaboration is continuing, so we're looking forward for future projects. And again, I want to thank all the people that attended the workshop, all the speakers, of course, technicians and admin people that helped behind the scenes for making this happening. And I want to thank all the people in the group, Eleonora, that lead this effort, and all the other people from our research group that made this symposium possible. Thank you, everybody.